this video is going to run through the entire history of the atom post-Dalton. So run through all the experiments that led to our understanding of the atomic theory, talk about the models, talk about how each theory for the scientists combined to give us our current model. So this video actually will cover 2 targets, and it's all of the history, so it's going to be a little bit longer. The main things to focus on when we talk about atomic history is, number 1, you need to know the experiments. What are the experiments that led to the creation of a new model? What evidence the experiment gave and how the model changed. So what's the experiment, what was the evidence, and how did the model change? After Dalton, the next experiment that happened was something called the cathode ray experiment. And this was Thomson, J.J. Thomson, that did the experimentation. Essentially what he did is he used cathode ray tubes, which was like a newer piece of equipment at the time. You send energy from one end of the tube to the other. There's nothing inside the tube that you can see, but you can see a light or some kind of basically screen that lights up when your ray of electricity runs across it. And what he did is he put a magnetic field across this invisible ray. And what he found when he did that was that the ray bent. Essentially, you can think of it like 2 magnets. He put a magnetic field over the ray, and it bent where the negative attracted to the positive side, and then the negative repelled away from the negative side. So his experiment was the cathode ray tube. The evidence he gathered was that an electric field caused the beam of light to bend. And this proved that the beam of light was charged, that there was some kind of charge inside of it that was causing it to be affected by that magnetic field. So essentially, he proved that there was some kind of teeny tiny invisible substance in here that was bending. They knew it was smaller than an atom based on how far it deflected. So essentially, they knew they'd found something smaller than the atom that must have been a component of the atom that was charged. They named it the electron, and they said the charge on it was negative. So the model that was created from Thomson's experiment is now the model using what Dalton had said, that there was an atom. So this circle idea, except it was no longer a solid sphere. There were now negative chips as part of the model. So sometimes it's called the plum pudding model, sometimes it's called the cookie dough model, sometimes it's called the muffin model, but essentially it's a mass of positive charged like mush, like pudding or the dough, with negative chips embedded in it. And those negative chips are much smaller than the positive mass. And that was the next step of the evolution of the atom. After Thomson's experiment, we had Rutherford's experiment. And what Rutherford found, he was working with radioactive materials, so substances that are naturally radioactive. And those substances, as they were producing rays, he directed those rays at a piece of gold foil. And gold you can actually pound so thin that it's essentially an atom thick. Okay, it's a couple atoms thick, but it's really thin. So his substance that was naturally producing radiation, the radiation it was producing were alpha rays. So he shot these alpha rays at gold foil. And what he found was most of those substances, most of those alpha particles, they passed straight through the gold foil. Okay? But some of them bounced off. Okay? So most of them came straight through, but some of them bounced straight off. And the analogy was like, it's like you're shooting a gun at a piece of paper and the bullet is literally hitting the paper and bouncing back at you, right? That's how it felt when he shot alpha particles at this gold foil, and most of them passed straight through, undeflected, but some of them shot back at him. And what he then postulated, so his experiment was the alpha particles with gold foil. The evidence he gathered was that most of the alpha particles went through, but some of them shot off at severe angles, some of them straight back at him. So the model that he proposed then was that the atom is actually consistent of some very concentrated positive mass in the center of the atom with kind of empty space where the alpha particles went straight through. So we call his model sometimes the nuclear model, where we have now a nucleus in the center, some kind of middle mass that's positive, and then these electrons, these negative chips, still there, but on the outside with lots and lots and lots of empty space. So when I think about his model, Thomson's model had the electron. Rutherford's model now has the nucleus and empty space. So he didn't really come up with a new subatomic particle, but he does propose basically this idea of the nucleus. Rutherford can also be contributed with helping discover the actual proton. He saw these really big hydrogen ions being produced when you shoot alpha particles into nitrogen gas. So again, he was working with these radioactive materials. And that ion was about the size of an atom, but it was positive in nature. So he essentially discovered a proton, because a hydrogen ion is just a proton in the nucleus. So he was able to say that that middle nucleus actually has like a positive particle in it. So now we have the electron, now we have the proton, now we have the nucleus. The neutron was discovered last and really late, right? It's hard to interact with the neutron because it's not charged. A man by the name of James Chadwick discovered it. He was dealing with barium radiation and parafilm wax, and he was able to find a subatomic particle that was non-charged but was the mass of the proton. Essentially, we knew the neutron existed at this time because the proton didn't account for all the mass of an atom, but James Chadwick was actually able to isolate and identify the neutron. So at this point now with our model, it's still kind of that nuclear model. In the nucleus, there are protons and our neutrons, and somewhere on the outside, we have the electron. All the rest of our experimentation was done on the electron. So Niels Bohr came next, and he was working with basically cathode ray tubes that were full of a specific element. So he was working with hydrogen atoms, and he would fill his cathode ray tube with hydrogen, again send the beam of light through, and this time the light actually was a visible beam traveling through the field of atoms, okay? And then even better, if you looked at that light through a spectroscope, you could actually see distinct bands of colored light being produced. And what he proposed was that there must be electrons there, but these electrons are actually absorbing and emitting light, only specific light, indicating the fact that there must be some kind of like energy hierarchy within the electrons. They're not just in this outer space area with the nuclear model, but they must be in specific regions to allow for only certain colors and the same colors every time for hydrogen. So if you did Bohr's experiment with like neon, there'd be a different spectrum than if you did hydrogen. So with Bohr, the model then became the solar system model. The idea that there are these concentric rings that electrons consist along, allowing them to jump up and fall down just very discrete amounts, and that accounts for the colored bands. So every jump up and then back down accounted for one specific light that was seen. After Bohr came someone called Schrödinger. Schrödinger took Bohr, took some of the issues with Bohr's model, took some of the experimentation that was happening with probability and statistics, and took our model to where we have it right now. Okay, they found that the electrons moving in an orbit around the nucleus using solar system model did not work in terms of the physics. So instead, they switched over to talking about electrons being in little regions of possibilities. So they came up with something called orbitals, which are probabilities of where electrons reside. So this is what the current model of the atom looks like. We still have our nucleus, our protons and neutrons. We still have our electrons on the outside, but our electrons exist in these orbitals rather than in specific concentric rings. So that's a blow through of all of the history. Again, you're focused on what was the experiment, what was the evidence gathered from that experiment, and how did the model shift. Have a nice night.